Good evening, class. We are looking at exam 3 review, chapter 3 differentiation rules, chapter 4 application of differentiations. And we have several parts. We're going to start with the first part, section 3.9, related rates. In short, we are looking at applications. We are looking at word problems. So we are going to cover from 3.9 to 3.11 and 4.1 to 4.5, and the rest of it will be covered in the next exam. So again, differentiation formulas starting with the definition. Limit of sine theta over theta as theta approaches 0 is 1. Limit of cosine theta minus 1 over theta as theta approaches 0 equals 0. And definition of a E in a couple of different formats is the limit of 1 plus 1 over n to the power of n as n approaches infinity, or is a number such that the limit of e to the power of h minus 1 over h as h approaches 0 equals 1. Different basic differentiation formulas, such as the constant, the power rule, and trigonometric functions. We add the product rule, the quotient rule, exponential functions, composite function, logs, and composite function give rise to the chain rule, and of course, inverse trigonometric functions. Now, related rates. If we are, just as an example, if you are pumping air into a balloon, both the volume and the radius of the balloon are increasing, and the rates of increase are related to each other. But it is much easier to measure directly the rate of increase of the volume than the rate of increase of the radius. In a related rates problem, the idea is to compute the rate of change of one quantity in terms of the rate of change of another quantity, which may be more easily measured. So what is the procedure? Number one, find an equation that relates the two quantities. Number two, use the chain rule to differentiate both sides with respect to time. Therefore, t is the independent variable, and dy dt is dy du dt based on Leibniz's notation. So as a warm-up example, air is being pumped into a spherical balloon so that its volume increases at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing? When the diameter is 50 centimeters. So it's important to understand what is given. And we verbalize that the rate of increase of the volume of air is given as 100 cubic centimeters. What is missing? The rate of increase of radius when the diameter is 50 centimeters. So that's fine, but how do we write this symbolically? First and foremost, remember a sphere is in this shape with the volume being 4/3 pi r cubed. D is 2 times r. The diameter is 2 times the radius. That's a piece of information we should have from algebra, geometry, you name it. So the formula that relates the two quantities, the volume and the radius, would be V equals 4/3 power cubed. Now, symbolically, what is this? The rate refers to the differentiation. dV dt is 100 cubic centimeters per second. What is missing? dr dt. When d is 50, r is half of that, 25 centimeters. So that is the translation into mathematical symbol. So I highly recommend any word problem, write the given symbolically. And remember, the independent variable is t. You're taking the derivative with respect to t. In essence, you want dv dt. And you can write it in this fashion. And notice dy dt is dy du du dt. So the intermediate variable from y to t is r. So dv dr dr dt. So what do? We are going to differentiate this with respect to t. So we start with dv dt equals 4/3 pi, because that's a number, that's a coefficient. It's not going to change. Differentiate r cubed, 3r squared dr dt, because you're taking the derivative with respect to t. And these two cancel each other. We get 4 pi r squared dr dt. And all we have to do, either plug in and find the missing one, or say dr dt is dv dt divided by 4 pi r squared. Makes no difference. Either way is fine. At this point, we are ready to move on. This was the only calculus step. And so replace the dv dt with 100 and r with 25. Remember, 4 times 25 is 100. This is, of course, 25 squared. So what happens is that you can say, okay, 4 times one of those 25 cancels this. We get 1/25 pi exactly. Always in calculus, keep it exact. Now, if you change it using a calculator, you end up with this number, 0.0127. Again, however many decimals they ask you. Units for the radius over the units for the time, centimeters per second. So the radius of the balloon is increasing. Why is that? Because this is positive. Otherwise, it's decreasing at this rate, 1/25 pi, which is roughly 0.127 centimeters per second. Again, very straightforward, everybody. A quick recap. Spherical balloon, we should, and the volume and the radius, we should know V is 4/3 pi cubed. dV dt is given. dr dt is missing when r is half of 50 or 25 centimeters. As long as you differentiate, the rest is elementary algebra. A small rock is dropped into a lake. Circular ripples spread over the surface with the radius of each circle increasing at a rate of 3/2 feet per second. Find the rate at which the area of a circle is changing when the radius is 4 feet. So what should we know? Here's a circular shape. We know the area is pi r squared. Starting from the center to the circle is the radius. Starting from the center, go both sides is the diameter. D is 2 times r. C going around the circle. Circumference is 2 pi r. The formula we need is A because dr dt is given. If you read the question again, with the radius of each circle increasing at this rate, that means dr dt. How do you know it's dr dt? Because of the word rate. Dr dt is 3/2 feet per second. What are we looking for? The rate at which the area is changing, dA dt. At what point? When the radius r equals 4 feet. So translation of this question into mathematical symbols would be A equals pi r squared. Dr dt is 3/2 feet per second. Find dA dt when r is 4 feet. You must know A is pi r squared, and you are going to differentiate that with respect to t. So dA dt is pi, because pi is a number, remains, and then now differentiate r squared, which is 2r dr dt. And you rewrite. You're done with calculus, you plug in, you're done. Replace the r with 4, dr dt with 3/2. Remember, this means 4 feet. This means 3/2 feet per second. Whatever we do to numbers, we do to units, so we get the proper unit back. And of course, we get 12 pi units of the area over the units of time, 12 pi square feet per second, which is an exact answer. Rough estimate, depending upon how many decimals they ask you, 37.6991 square feet per second. You must always answer exact unless they ask you otherwise. In your work, you must always have the exact anyways. A quick recap. As we read the question, circles, the relationship between radius and area, you need this formula, A equals pi r squared. Then this one is the rate for the radius dr dt, and this one is the rate for the area dA dt missing, and the radius is 4 feet. A 20-foot ladder leans against the building. So that's the building or the wall. This is the ladder. The base of the ladder slips away at a rate of 2 feet per minute. So it's going to move that way at a rate of 2 feet per minute, which creates this shape. So this is going this way. This is coming down. As it moves this way, it creates the speed or rate of 2 feet per minute. And ladder is fixed at 20 feet. So this doesn't change. This one or doesn't matter how far it goes. This is fixed at 20 feet. But it creates the speed of 2 feet per minute. Find the rate of change of the height of the ladder. So this is coming down. As it moves down, creates the speed or rate of dy dt. I'm defining each variable, and that's exactly what you should do with word problems. You draw the setting, you define your variables, and we want to find this at what point when the base is x, is 12 feet from the building, when x is 12 feet. So in order to relate the quantities, namely x and y in order to go from dx dt to dy dt, we need a formula. First, I'm going to remind you, this is a right triangle. Pythagorean theorem says a squared plus b squared equals c squared. This is a right triangle. So for this would be x squared plus y squared equals c squared, which is 20 squared. So we're going to write dx dt is 2 feet per minute. The formula is x squared plus y squared equals 20 squared. dy dt is of interest at a precise moment when x is 12 feet. So we write dx dt is 2 feet per minute. X squared plus y squared is 20 squared. Dy dt is missing when x is 12. That's how you write this. And if you can translate this into the symbolic format here, you've done most of the work, everybody. So obviously 20 squared is 400. It's just a number. So we are going to differentiate this with respect to t. This becomes 2x dx dt plus 2y dy dt equals any number gives you 0. So we have everything we can plug in. The only thing we notice, y is missing. So at the moment that x is 12, put it in Pythagorean theorem, x squared plus y squared equals 20 squared. Which means 400. Subtract 144 from it. You get 256. Y squared is 256. Y is 16 feet. Now you have everything. Replace everything. The only thing missing is dy dt. Two times 12 times 2 is 48. 2 times 16 is 32. We are going to move the 48 and make a negative on the right side. Again, everything becomes elementary algebra. Divide by 32. Both numbers are divisible by 16. You get negative 3 halves feet per minute. Feet per minute. Units of the numerator over the units of the denominator. Change in y over change in time. Negative 3 halves feet per minute. A couple of notes. Number one, x is increasing. Dx dt must be positive. Y is decreasing. Dy dt must be negative. So that is important to understand. Number two, if somebody says, okay, put it in writing, then you would say, at the moment when the base is 12 feet, it slips down at a rate of 3 halves feet per minute, or it's decreasing, okay? So when it's increasing means positive, decreasing means negative. Now, a quick recap is reading this drawing. If you don't do the drawing, there is no way to solve this without drawing and defining your variables. And in this case, we need Pythagorean theorem. Now, I'm going to repeat the same question. Please understand, as this thing happened, this angle changes. So does this angle. So we can go to the same question and now ask what happens to the angle. This one is between the ladder and the ground. This one is between the ladder and the building. So it depends what they ask. Both are changing. So here's the next question, in essence, part B. Same question, a 20-foot ladder leans against the building. The base of a ladder slips away at a rate of 2 feet per minute. Find the rate of change of the angle between what? The ladder and the ground when the base is 12 feet from the building. So the same thing here, moving this way, creating this shape. And now as it comes down, it has a fixed hypotenuse of 20 feet. This is the angle between the ladder and the ground. We could have asked for this one, okay? So pay attention, this part you got to read to see which one they are referring to. This angle is changing. So we know dx dt is 2 feet, just as before. Now we are looking for d theta dt. And everything is the same as the previous one, except d theta dt is missing. So I would write everything the same, just as before. And I'm going to add, okay, this is what's missing. And I need to relate variables such that I can find this. So what variables are we relating? We have to somehow relate x and theta, yx, because dx dt is given. One might say, okay, I can relate y and theta because I've already found dy dt in the previous part, and you're 100% right. However, what if we made a mistake? You always work with the given if possible. So what is the relationship between x and theta? As you can see, cosine theta is the adjacent x over the hypotenuse 20. Sine theta is the opposite y over the hypotenuse 20. So we need to know both of them. This is x over 20. This is y over 20. And because dx dt is known, we are going to use this one. We could use this one and the fact that we have dy dt from before. But we're going to use this one because we don't need that. Dx dt is needed and is known. So cosine theta is x over 20. That's what we are going to use. And before we differentiate that, I want to make sure that you notice this means 1 over 20 times x, which means when you differentiate the right side, just bear in mind this is 120, and then you differentiate x. So what happens on the left side? The derivative of cosine is negative sine. So you have negative sine theta d theta dt, because theta is not the independent variable. In related rates, only t is the independent variable. The right side is 1 over 20, x is dx dt. So 1 over 20 dx dt. So now we can plug in everything that we have and find the missing one. We have dx dt, so I can replace it with 2. But we don't have the sine. We know sine is y over 20. So we are going to change it to y over 20. So minus, instead of sine, we're going to say y over 20. And now recall that y was 16. We are going to replace the y with 16, dx dt with 2. So please understand, this is the extent of calculus. Everything else is algebra, geometry, trigonometry, you name it. Now, we do this, and rather than saying multiplying by 20, notice you can drop the 20, everybody, because it's identical denominator. You can drop it. So minus 16 d theta dt is equal to 1 times 2 or 2 divide by negative 16. You get negative 1 over 8. So d theta dt is negative 1 over 8 radians per minute. Units of angles are always radians unless otherwise mentioned in calculus. So negative 1 over 8 radians per minute. What does it mean? Obviously, x is getting larger, dx dt is positive. Y is getting smaller, dy dt was negative. What about theta? I hope you can see that theta is here and it's becoming smaller and smaller and smaller. That's why it's negative. On the other hand, this angle, if you call it alpha, let's just give it a name. It's here, then it's here, and it comes down. As it moves down, this alpha gets larger and larger. If you were to calculate that one, in other words, the alpha dt, that would be positive. Example 4. Falling sand is forming a cone-shaped pipe. The volume of the cone is increasing at a rate of 54 pi cubic inches per minute. So we're going to stop here. Cone shaped, this is the shape. You should do the drawing. You should let your reader see the type of three-dimensional, uh, quantity that you're working with, and the volume is 1/3 power squared h. This is a piece of information which is a prior knowledge of mathematics. You have to do the drawing and this one. Now, the height of the cone is twice the radius. That means h is 2r. H is 2r. Find the rate at which the radius changes when the radius is 6 inches. So the volume is 1/3 power squared h. It's increasing at this rate. dV dt is 54 pi cubic inches per minute. H is 2r. The rate of radius, that means dr dt is missing at which point? R is equal to 6 inches. So this is the given, everybody. So one more time. This is a formula we should know. The volume is 1/3 power squared h. dV dt is 54 pi cubic inches per minute. H is 2r. dr dt is missing. R is 6 inches. Now, this one has two variables, r and h. We are going to use this formula to get rid of one of them. Because we want dr dt, we're going to keep the r and we're going to get rid of the h, replace it with 2r. Now, if the question is asking for dh dt, and I highly recommend you try this on your own, in other words, find the rate at which the height changes for the same question. If you need dh dt, when you go to this question, then you keep the h, you change the r. What do you change it? If h is 2r, r is h over 2. This means r is h over 2. You can change it here. Anyways, this one will result in 2/3 pi r cubed. Everything so far we've done is just algebra. We are writing the given and the algebra, and now differentiation, dv dt. We keep the 2/3 pi because it's a number, and we just differentiate r cubed, which gives us 3r squared dr dt. Gives us this one, 3r squared dr dt. These two cancel each other. We get 2 pi r squared dr dt. So what is dv dt? Replace it with 54 pi cubic inches per minute equals 2 pi r 6 squared. So replace that one. And find the missing dr dt. Now, of course, this is 54 pi, this is 36. Times 2 pi is 72 pi. And divide both sides by 72 pi. Divide this one by 72 pi, it goes away. This one by 72 pi. The pi's cancel out. These two numbers are both divisible by 18. The numerator becomes 3, the denominator becomes 4, and the units of r over the units of t, 3/4 of an inch per minute. Bear in mind, this was cubic inches. Now, of course, if you write here, instead of 6, write 6 inches quantity squared, and instead of just dr dt, instead of 54 pi, write cubic inches per minute, you see that it works out. So whatever you do to numbers, you do to units, and it works out. Dr dt is 3/4 of an inch per minute. Again, I highly recommend that you try to find dh dt as well. And at this point, there are two different ways. Example 5. At noon, ship A is 100 kilometers west of ship B. Ship A is sailing east at 35 kilometers per hour, and ship B is sailing north at 25 kilometers per hour. How fast is the distance between the ships changing at 4 p.m., meaning 4 hours later? Let's see what we need to do. At noon, we read it a couple of times and we go back. At noon, ship A is 150 kilometers west of ship B. So we have A, we have the B, and the distance is whatever that they mentioned here, 150 kilometers. So at noon, let A sub 0 be the position of ship A, B sub 0 be the position of ship B, and their distance is how much? 150 kilometers. Again, you have to draw the setting to have an understanding as to what's happening. So this is moving this way. Ship A is sailing east to the right, and that's the speed, 35 kilometers per hour. Ship B is going up north at 25 kilometers per hour. A moves east at 35 kilometers per hour. Let X be the distance traveled by A at time t. Similarly, B moves north at 25 kilometers per hour. Let Y be the distance traveled by B at any given time t. So if that is the case, notice what happens. So we start from here, we are moving this way, we get this far. And if this is the covered distance of x, what is left? If the total is 150, 150 minus x is left. So one more time. Total is 150 from here to here. X amount is covered. What is left here? 150. So we are going to call this 150 minus x because the entire distance is 150. We're going to call this distance bb0y, and this distance, we're going to call it z. So you are defining your variables. And the x dt, so this means the x dt because it's moving at 35 miles per hour, and y means dy dt, 25 miles per hour. So dx dt is 35, dy dt is 25. A has sailed east x miles. The remaining distance is 150 miles. So all we did so far, we explained the question. Now we are ready to relate variables by writing formulas. To do so, Pythagorean theorem applies to this. Because this is a right triangle. A squared plus b squared equals c squared. So this side is 150 minus x, quantity squared. This side is y squared equals hypotenuse z squared. That's what we are going to use. But we are going to rewrite this information as follows. Dx dt is 35 kilometers per hour. Dy dt is 25 kilometers per hour. T is 4, y is t4 from noon to 4 p.m. Find dz dt. So we're going to write 150 minus x quantity squared plus y squared equals z squared. And we are going to differentiate. All of this explanation was to make sure we understand how we arrive at this equation, which is Pythagorean theorem. Now, one step of calculus is differentiation. How do you differentiate this with respect to time? Okay, 2 times 150 minus x to the power of 1 times the derivative of the inside, which is minus dx dt, plus 2y dy dt equals 2z dz dt. Done. Calculus is finished. Plug in and you're done. So in order to plug in, we need to know over the course of 4 hours, what is the distance of x and y. At 4 p.m., we have covered 4 times the speed for x and for y, 4 times the speed of the y. So at 4 p.m. is 4 times 35, 4 times 25. Those are the coverage. So we have covered x amount is 140 and y amount is 100 kilometers. So into this formula, if I plug in, I can find the z for this case as well. So I'm going to write 150 minus x, which is 140 quantity squared, plus y squared, which is 100 squared, equals z squared. I want to find z. This is obviously 10. You square it, you get 100. So this is 100. This is 10,000. So they add up to 10,100. So z is the square root of 10,100. I'm assuming nobody has any problem with this stuff. Okay, so it's elementary algebra. So z is, again, I'm using the precise answer. Ultimately, you use a approximation, but please wait until the last moment. You don't want to have any intermediate step. And so plug in, replace everything. So what do we replace with? X, we replace it with 140. okay, minus dx dt, 35, so minus 35. 2 times y is 100. dy dt is 25. 2 times z, which is this number, square root of 10,100, dz dt. Now, just plug it into a calculator. I hope you realize this one as a 10, again, as I mentioned, times negative 35 is negative 350. And by the way, you notice that there are twos on both sides. You can get rid of them, right? That's one easy way. Then this is negative 350, and this is 2,500. Let me make sure everybody understands what happens here. 2 here, 2 here, 2 here. I'm factoring out the 2 in essence. This one is 10 times negative 35 is negative 350. This one is 100 times 25, 2,500. These two numbers, they add up to 2,150. So dz dt would be 2,150, everybody, divided by the square root of 10,100. And that's an exact answer. Put it into a calculator. You get 21.4 kilometers per hour. Okay, easy, ET. So let's recap quickly. From noon to 4 p.m. T is 4. Ship A is doing dx dt. We have defined, okay, the coverage by ship A as X, the coverage by ship B as Y. That's why if this is X, dx dt is 35 kilometers per hour, dy dt is 25 kilometers per hour. It's very important to do that. And T is 4 because from noon to 4, and we want dz dt. And this uses Pythagorean theorem, 150 minus x quantity squared plus y squared equals z squared. The rest is just very basic. The hardest part is to find this equation. Even differentiation is very easy. A spotlight on the ground shines on a wall 12 meters away. If a man 2 meters tall walks from the spotlight toward the building at a speed of 1.6 millimeters per second, how fast is the length of his shadow on the building decreasing when he is 4 meters from the building? We need to do the drawing, okay? So the idea is that you have a spotlight and you have a wall. This is spotlight and this is a wall and it's shining. Now the distance is 12 and there's a guy 2 meters tall that it's moving towards that. And as it hits the guys, as he moves, this shrinks. So spotlight is somewhere here. The man is walking towards the wall. This distance is 12 meters. It covers so much. As it moves this way, you can call it x, then the speed would be dx dt, 1.6 meters per second. So it creates this shape. So the spotlight is here, the wall is here, and this is where you shine it against the wall. Then the guy shows up 2 meters long and walks towards the wall. So as you can see, it this thing moves, it actually moves down, it shrinks. That's why they say decreasing. So the man is 2 meters. as, and the whole thing is 12 meters to be covered. So as he moves, he covers X amount. His height is 2. And at the moment that he covers X amount, the shadow is Y amount. You have to define your variables. So if this is X, this is 12 minus X. So if this is X, this must be 12 minus X. When the man covers X feet, his speed is dx dt. So his speed is dx dt. So dx dt is 1.6 meters per second. We want dy dt. At what point? When he's 4 meters from the building. So if he's 4 meters from the building, that means 12 minus x is 4. That means x must be 8. Dx dt is 1.6 meters per second. Dy dt is missing. When he is 4 meters from the building, that means 12 minus x is 4. That makes x 8. Okay, that's important to pay attention to the readings. So I hope you recognize the small triangle and the large one. They are similar triangles. So what are similar figures? Reminding everybody about similar figures. Corresponding angles are identical. Look at corresponding angles. This one is in common. This one is 90 degrees. This one is 90 degrees. If two angles are equal, then the third one has no choice but to be equal because the sum is 180. So this angle and this angle are equal. When we have two parallel lines, that's what happens, okay? So this is in common. This is 90 degrees. This is 90 degrees. These two become identical. So corresponding angles are identical or equal. And corresponding sides are in proportion. So you can pick a side from the smaller one, pick a side from the larger one, or two sides from the smaller one to two sides from the larger one. It doesn't matter. So the small one and the big one are similar figures. So if you go with the big one and say y, compare it to 12, then would be 2 compared to x. I hope you see this is one way to write it. So take a look. Y is from the big one, and in front of that 2 is from the small one. 12 from the big one, x from the small one. There are different ways of writing it. That's one way to do it. So this is the hardest part, figuring this out. And of course, if you do the cross product, you get y equals 24 over x or 24x to the power minus 1. The only reason I'm doing this, so I get this ready for the next step, which is differentiation. So far, we just found a relationship between the two, and we are going to differentiate to find dy dt. So what is dy dt? 24 times, now differentiate this one. I want to differentiate this. Dy dt is 24 times negative 1 x to the power of minus 2, which, and dx dt, dx dt. I thought I mentioned that, but I didn't. So minus 24 over x squared, that's the derivative of 24 x to the power minus 1, and dx dt because the independent variable is t. So we replace the x with 8 and dx dt with 1.6. I hope you see that 24 is divisible by 8. So I can change the 24 to 3, and 8 times 8 just becomes 8. 1.6 divided by 8, imagine is 16 divided by 8 is 2, so it's 0.2. So 3 times 0.2 is 0.6. Negative sign makes it negative 0.6 meters per second, which means the length of his shadow is decreasing at the rate of 0.6 meters per second. When you're explaining your in words, decreasing covers the sign negative, okay? Increasing covers the sign positive. A quick recap. We have a spotlight and we have a building or a wall. A man starts walking this way towards the wall. As you can see, then the shadow which has the height of y, we called it, is shrinking. So the man is 2 meters tall. When the man covers X amount and is doing 1.6 meters per second, we call it dx dt. Because we call this X, then this is dx dt. If you call this Z, dz dt. If you call this A, dA dt. That's why you need your variables and you need the drawing and setting. So the entire distance is 12. So when we cover X, what is left? 12 minus X. And it says 4 meters from the building. That means 12 minus X is 4. So X is 8. And now the small triangle compared to the large one, they are similar figures. And we write y over 12 equals 2 over X and differentiate. A cylindrical tank with radius 10 meters is being filled with water at a rate of 7 cubic meters per minute. How fast is the height of the water increasing? Draw a diagram, include units. Even if they don't ask you that, you really must, because you're dealing with word problems. So here's a cylindrical tank. Here's the height. Here's the radius. And the radius is fixed at 10 meters. How fast is the height changing when we are filling up the water by this rate, 7 cubic meters per minute? That means immediately we need a formula for the volume of a cylindrical shape, which we should know is pi r squared h. Pi r squared h. And this is dv dt, 7 cubic meters per minute. R is 10 meters. How fast is the height increasing? The h dt is missing. So we write the volume is pi r squared h. We should know this formula. dv dt is given. R is fixed at 10 meters and dh dt is missing. Couple of different ways quickly we can look at that. because R is fixed, and you can call it just capital R because they don't even have to give you that. And then you work with R, okay? So dv dt is pi r squared times dh dt. dv dt is pi r squared times, now h is a variable, dh dt. dv dt can be replaced by 7. Capital R can be replaced by 10, and you can do that in the beginning. So I will show that way too. So obviously this is 100 pi. So divide by 100 pi. dh dt is 7 divided by 100 pi. And again, this is an exact answer. Units of the height over the units of the time. Meters per minute. This was cubic meters. That means this is in meters. 7 over 100 pi meters per minute. The other one is that right here, everybody, change the R to 10. 10 squared is 100 and deal with 100 pi. So I'm changing this to 10. So now, if you want to differentiate this, 100 pi is just a fixed number, is a coefficient, so times dh dt. If you find this easier, you can go with that. If the minute hand of a clock has length r in centimeters, find the rate at which it sweeps out area as a function of theta. So here's a circular shape, central angle theta, radius r. So this distance is called S equals r theta. This area is called area of a sector, half of r squared theta. So information from trigonometry. So one more time, a circular shape, radius r. This is a central angle theta. It covers this much. Arc, this arc length S equals r theta. This is a sector. Area of a sector, half of r squared theta. So A is 1/2 r squared theta. We want dA dt, and r is fixed because it's a minute hand of a clock. It will never change. So although it seems to be a function of two variables, r and theta, but r is fixed. R is some number. We may not know what is the length, but it doesn't change. So when you want to differentiate, dA dt is still this one times all you have to do differentiate theta, and you get 1/2 r squared times d theta dt. Believe it or not, this is done, but I want to make more sense out of it by looking at a specific example. For example, in 1 hour, the minute hand covers what? A complete revolution of 360 degrees or 2 pi radians per hour. So d theta dt in 1 hour is 2 pi radians, again, a complete revolution, 360 degrees, or 2 pi radians per hour. So dA dt is half of r squared, d theta dt is 2 pi. or pi r squared? Because this is in centimeters, centimeters squared per hour, because units of the area. Remember, this is in centimeters. If it's not given, you don't have a unit. It's units of the area over units of time. Okay. Another example, in one day or 24 hours, the minute hand covers the same thing times 24. So it covers the same thing times 24, which means 24 times 2 pi, or 48 pi radians per day. So in this case, we are going to replace this one with 24 times 2 pi, which is 48 pi radians per day. So we get 1/2 r squared times 48 pi. 48 cancels out to 2, becomes 24 pi r squared. Same unit, centimeter squared, but hours now it's day, per day. So slightly different unit because it's per day. A street light is mounted at the top of a 15-foot tall pole. A man 6 feet tall walks away from the pole with a speed of 5 feet per second along a straight path. How fast is the tip of his shadow moving when he's 40 feet from the pole? The drawing is important. So we have a 15 feet tall pole, and a man which is 6 feet is going to move away, walk away from it. So it looks something like this. This is the pole, 15 feet. This is the man, 6 feet, is moving this way, and he is moving at a speed of 5 feet per second. So again, 15 feet, the height is 6 feet, and he's moving at the speed of 5 feet per second. We're going to call it dx dt. So as he moves, the tip of his shadow is here. So tip of his man, the man's shadow is here. So when he covers this much, which we are going to define it, for example, X, the tip of the shadow covers this much, which we are going to define it, for example, Y. So when the man covers X feet, his shadow covers Y feet. So dx dt is going this way with the speed of 5 feet per second. Dx dt is 5 feet per second, but we don't know what dy dt, because it says how fast is the tip of his shadow moving, dy dt. At what point? When he's 40 feet from the pole, when this distance He is at x equals 40 feet. This is understanding the problem. You have to define your variables. You have to draw the setting so you make it clear as to what's going on. So obviously, this looks like two triangles. This one is 15, this one is 6, this is x, the large one is y, and again, small one and the large one are similar triangles. Therefore, we can say, for example, 6 to 15 is the same as this distance. The smaller one is this distance, which is y minus x, to the big one, which is y. So the small one, 6 to 15, the small one, y minus x, to the large one. Why it's important to know this is x, this is y, so this is y minus x. And so you do, this is really the hardest part, figuring this one out. And now to differentiate first, we are going to do the cross product. 15 times y minus x is 6 times y. Which we get 15y minus 15x. We move this to the right, becomes positive. This one to the left becomes negative. So we can combine into 9y equals 15x. Divide both sides by 9, y is 5/3 x. Now we are ready to differentiate. dy dt is 5/3 dx dt. dy dt is 5/3 dx dt, and we have dx dt as 5, so we get 25/3, same unit, feet per second. A quick recap. So we have a 15-foot pole. There is a street light here shining on the guy. As he moves from here, he covers X amount. The tip of his shadow covers Y amount. That's really the key. So if this is X, this is Y. So this is X, this is Y. And obviously this distance is Y minus X. And the two figures are similar figures. So the ratio of 6 to 15 is the same as Y minus X over Y. And that's not the only way to write it. There are several ways. When you get here, the rest becomes easy. Cross product, you can solve for y and then differentiate both sides with respect to t. Remember, related rates, t is the only independent variable. A spherical balloon is deflating, losing 8 cubic centimeters of air per minute at the moment when the radius of the balloon is 20 centimeters. How fast is the radius decreasing? Again, I'm reminding you that the volume is 4 meters per cube. You really should know that. Now, the purpose of this question is just to pay attention to this. This means negative. So the volume is 4 meters per cube. dV dt is negative 8 cubic centimeters per minute. We want dr dt when r is 20 centimeters. So this is translation of the entire question with the addition of the formula that we should know. So this is supposedly it's not given. The volume is 4 meters per cube. dV dt is negative. Why negative? Because it's deflating, losing, minus 8 cubic centimeters per minute. We want dr dt when the radius is given to be 20 centimeters. So to differentiate this, you have 4 thirds pi that is a number and it's not going to go away. And then you multiply by the derivative of r cubed, which is 3r squared dr dt. So just this one, okay? And these two cancel each other. I hope we remember this. It was 4 pi r squared dr dt. So you can solve for dr dt. You just plug in, again, a slightly different methodology. Just plug in. You have dv dt as -8 or as 20. And so when you score the 20, you get 400 times 4 is 1600. So the right side is 1600 pi. We are going to divide both sides by 1600 pi to get the RDT. So 8 becomes 1, 16 becomes 2. So -1 over 200 pi. And the units of the radius over the units of time, centimeters per minute. Again, an approximation if they ask you, otherwise you don't have to put it into a calculator. You get negative 0.001592 centimeters per minute. As you can see, I have many decimals depending upon how many they ask you.